So I mean, that's our concept is there's objective reality to what happens in the universe, right? As opposed to just our universe. So the question is, in what sense might it be the case? I'm looking for a case where we can clearly see okay, here's a trivial example.
Of
Trivial
what?
example of this phenomenon. Okay, so trivial example. What if we live near a black hole?
Hmm.
Then and we used a different, different time coordinate system and so on.
Okay.
I'm still struggling with the thing.
No, hold on. What, Stephen? What are you trying to explore? Because you haven't. You've
Okay,
been
I
kind of
haven't
thinking
finished the
aloud, but
sentence.
you
I
haven't
haven't
explained
finished
it
the
to me.
sentence. Yeah,
Yeah.
right. Okay. So one point of view is there's an objective reality to what's happening in the universe.
Hmm.
Another, which is our current point of view, is all reality is subjective. And my question is, what will cause one? Okay, so the claim is all physical reality is ultimately subjective, i.e., depends on what the observer measures, aggregates, samples. Okay.
Yeah. Yeah. Yes.
Okay, but that's very different from the current theory idea of physics.
Yes.
Although there are glimmerings of it in general relativity already.
But what's
because of different reference frames.
what's the question that you want?
Okay, the question that I want to ask.
You want an example of what?
I want an example of a place where it's clear that the physical reality is subjective, that where the laws of physics, where nobody will be surprised that laws of physics changed as a result of the choices of the observer.
Well, a black hole seems like a good place to start.
Yeah, I kind of agree. So the preferences in an observer yeah, I'm not sure I can immediately come up with how that will work. Okay, while we're on the subject of finding explicit examples, what about an example of where we end up with that incompatibility of mathematical paths? Okay, so we want We want an example in mathematics. Actually, I don't think this is that hard to get, right? Because, I mean,
no,
I think even if we just say, okay, let's look at a very trivial example.
Like numerical multi-computation.
That's a possible case. Let me think about that one.
And that's kind of why you did it, right? Was to invest in a kind of case of simple examples.
Yeah, no, I agree, but I think that there may be an even simpler case here. Let's take, for example, this guy. Okay, so that's got multiple paths, obviously. And the issue is, we go down this path, we go down some path here. It's by no means obvious that you can get from one of these to another.
You mean like at the time, you mean? Like when you're at one particular position? I mean, just staring at it, you can see where the paths go.
No, I know, but ABB and BAB, they converge, but I don't think you can you get from ABB to BAB? I don't think you can. I don't think you can. I think you go forwards in time.
You're asking if you can get one from one to the other without going forwards in time?
No, I'm asking if there's a path whose end point is BAB. ABB, look, the question is, can you go from AAB and the answer is no, because this thing never goes back, right? It doesn't go back to BAB, does it? It won't generate BAB at a subsequent step.
It doesn't look like it.
No, I don't think it does.
No.
So that's an example of a case where you can't get.
You need to have you need to have AB goes to BA or something like that. We don't have that.
Right. Well, so if we take a system like
and didn't you describe at some point these kinds of splits as black holes as well? It's not quite the same.
In the causal graph.
Yeah.
Okay, so here we've got AABBAB. Oh, I see. We can't get in this one, we're going one way. But assuming we had the other way rule, right, now we can get between any two cases.
Sure. Yep.
So,
well, because we basically have a closure property now.
Yeah. Yeah, we can get from anything to anything right now.
Yeah. So now it's more like we're.
But you see, what seems to be generic is that you can wind up in incompatible states. That's generic.
That's generic. Yeah. Yeah. Okay.
Happens often, right?
Yeah. Yeah.
And so the claim is this is the kind of that, these are space-like separated things, or branch-like separated things. And you can kind of wind up with them separately. Well, all right, I'm sort of understanding this. I'm sort of understanding that in mathematics, let's see, the analog oh, I'm slightly confused. But okay, so a different thing I think I had in my previous discussions here. Actually, what I really want to do is to color these pictures by the different rules they use.
Yeah.
Do you know how to do that? I wonder if multi-way system has an approach to doing that.
Well, didn't you do that in the numerical multi-computation post, basically?
Yes, I did, but that was using different code.
Yeah.
I can do that again. Yeah, I will do that again. Here it is. So this is an example. That's multiplication.
Hmm. All right. I found that division looks pretty interesting in the multi-way systems as well.
Why does it even converge? I mean, why does it have? I don't understand how you get division. I mean, this is showing that there are different rules here. There are 4 different rules here. I wonder what happens if I do just addition.
Hmm.
Why isn't that? That's much more straightforward. Why is that? This one is complicated because it's like primes, I think.
What are we looking for right now?
We're looking for an example which I can use to show how the Roolead is constructed. To show what a set of possible rules, what happens when you enumerate a set of possible rules. Okay, and here,
yes,
we're saying
where you get distinct outcomes depending on the rule that you take.
well, some outcomes are distinct.
Sorry?
Some outcomes are distinct.
Yeah.
But I mean, my point is, what are the slices here? What is the branch hill space here? I think I had some pictures of that in the numerical multiway document. God, there's a bunch of wild stuff here. Look at all that wild stuff. Isn't that officially wild?
Yes. Wow. Did you see that? Did you expect that, or was that a surprise when you found the Sierpinski gasket there?
I expected it.
Wow. Okay. Well,
You know, for people not schooled in this paradigm, looking at this document, it just must be very bizarre.
yeah.
What the hell is all this stuff? Okay, so I don't
It helps when you have like an echo function or something. You can yes, like this. I mean, with this kind of representation where someone gets the sense that, oh, okay, I mean, they probably even they can't follow that, but they can at least see that there's some process by which you get this kind of behavior. When you just see
they
it
can
all at
see
once, when you
the
see it at
device.
like the 20th step without seeing any other steps, you might think, oh, what?
Well, I mean, but this picture, you can kind of see these are the divisors.
Yeah.
Okay, what I'm trying to work out is the branch shell version of this.
Did you find it in that post?
No, I didn't. I don't think I did it in this post.
Oh,
I thought I discussed it at the end, and I discussed
branch shield space and numerical value space. Yeah, there's a whole section.
Oh.
Yeah.
I thought I'd discussed it. I'm not losing my mind.
I just searched for branch shield space. I found it instantly. Command F branch shield space.
Okay. Oh, I see. There we go. Okay, so this is what we want then. We've got this picture. You know, I've told these people not to do this. Oh, for God's sake. How many times do I have to tell them not to do it?
What?
The click to copy still has its output. I've told them not to do that.
Oh, I see. Yeah. Okay.
Okay. So here, I see. So that was just literally doing it like that. But these edges, okay, so let's give this version here.
Yeah.
Oh, Hunkadorasaurus.
It's a very British dinosaur.
Yeah. Okay, what is this? Two, three, 4, 4, 6, 8. So what are these things? These things are laying out values. I
Yeah.
see. This is in some kind of factorization space. And we can see how the rule add limits here. Okay, so this is essentially things are being laid out here in factorization space. Now, what we could do, so one form of limiting is we just increase the number of rules. I think we could do completions here as well. So we just increase the number of rules.
Okay. Mm.
Oh my gosh, look at these. What
Hey,
are these creatures?
that is, look at that. That's that second one is very interesting.
Tetrahedron.
Hey.
The Sierpinski-esque tetrahedron. Weird. All right, I want to try a different thing. I want to try doing these up to a much bigger number here, and then deleting every node that's bigger than a certain value.
Why?
Because that's doing the limit in a different order. You see. Look, we've got two limits going on here. We've got increasing the rule count. Okay, we've got, different limits. We've got number of rules. We've got time steps. And we've got initial conditions.
Yes.
Right, now here we didn't really have anything with the initial conditions. So if we do the corresponding thing with the initial conditions, we're saying instead of 1, let's see what happens if we take, so now,
yes.
In this case, that makes no difference.
You want to do a different rule?
No, I mean, yes, we could do that, but I mean, that will now generate 2 cases.
Well,
because we have more initial conditions. If we have more initial conditions than can be readily reached by the rules,
yes, right.
We have quotes initial dust
over,
which is knitted together only by the rules. Okay, so we've got number of rules, time steps, initial conditions. We've also in this case, we can say also limit here by state value. Okay, so the thing that I'm looking for here, here's the thing I'm looking for. This space that we're drawing here
Mhm.
is rulal space. I wonder if I actually can do this. Is there a rulal graph? Splatteroo. I thought we had the rulal graph stuff in there. We had a rulal graph. Oh, no, I see. The difference here is, oh yeah, we need the rulal. Okay, wait a minute. There's the rulal graph. Oh, what the hell? I'm just going to cheat. That's because it bothers me to see branchial colors there. Because they're not branchial, really. It's really real.
Okay.
So the issue is, in this layout in rulal space, can I identify in different regions of the space, can I identify that 64 is the thing I got by applying one rule a bunch of times? This 48 by something else. In other words, is this layout something where in different regions of this, I used a different rule to get there? Get what I'm saying?
Yeah.
That's the relationship between rulal space. That's what it means to say there is a space of states that are laid out in rulal space. That there are different rules required getting to different sections of this. So in other words, the 64 yeah, I mean, this is literally the factorization gives you what its rule specification was.
Yeah.
Right, but it's the factorization. I see. Look, given the factorization, actually, it's not really the factorization. It's really divisors of 48, let's say. Okay, so now what it really is the possible how one got there rules are the subsets that make 48. So it's kind of like the multiplicative partitions of 48. Do you see what I'm saying by that?
Yes. They're the
How do I get those?
all the possible rulal histories that lead you to 48.
Yeah, right. All rulal histories.
There are many, especially if you account for different different initial conditions, right?
Well, let's
49 minus 1.
No. This is all multiplication.
Oh, just multiplication. Oh, that's much easier.
Right. This is things of the form. Okay, so what we've got is a product of A sub I, basically starting with the initial condition, whatever the initial condition is. We won't worry about that for a second.
Right.
It's product of A sub I up to whatever it's up to, right? It's just something like that. And the question is, what products, okay, what products of integers lead to 48?
Okay. So 3 times 4 times 4.
Okay, I understand, but how do we compute that? How do we compute that? What it is we take factor integer
Yep.
for 48.
Okay.
And then what we do is we have to apply to that table
Okay.
of hash triple at that. Oh, silly me. Okay, there it is.
Yeah.
Then we say, okay, here's what we do. Okay, so then we find this integer n. Then we flatten this. That's all the prime factors.
Okay. Okay.
Okay, so now what we do is we take the subsets of that. No.
Well,
we take all possible partitions of that. We take all possible ways to partition that into at most n things. How do we compute that? How do we compute all possible partitions? It's not subsets because right? We need.
No, it can't be the subset of it.
No, right. But in each one, it's just a way of grouping. Oh, is it groupings?
Yeah, it could be groupings.
No, it isn't. It isn't. It's all possible ways to put parentheses. It's all possible ways to pick every element out of here.
Well,
right?
Yeah. Otherwise, you won't get 48. Multiplicative.
Exactly. Right. Right. You have to pick all possible ways to pick every element out of that. All possible groupings of that. That pick out every element. Oh God, this is a trivial thing. What the hell is this? All possible groupings. All possible ways to parenthesize this. Or ways to pick out every element in this without. Okay, so basically what we need to do. Yeah,
you want to multiply some of them, right? So you can get like a 6 or a 4.
No, I know. So all we want to do is we want to have an indicator function. Okay, this is what we want to do.
Okay.
At each stage, okay, imagine we want to assign a layer number to this in all possible ways. Okay, so assume we've got 3 layers. I see, but many of these are the same because those numbers are the same.
Yes.
Right, so what we want to do is we want to say, okay, so then we want to say, with, well, multiplicative parts of 48. Okay, so now we want to say, possible rule sequences. Well, multiplication sequences of n is with facts equals multiplicative parts of n. Okay, so now what we want to do well, one way we can do it is we can say tuples of range of P comma length of n, length of facts and then we want to say facts of that, then we want to union that. Okay, so now we say multiplication sequences of 48, 3. Oh, I need to say extract here, I think. That's profoundly wrong. Oh, no, 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 no. This is the wrong way to do it. This is giving us to what layer each number is assigned. Okay, do you get what I'm saying?
Okay.
So, for example, we might assign this. This might be 1, 1, 3, 2, 1. Okay?
Yeah.
So then what we want to pick out how do we say that? We want to pick out all the ones Oh, I see. What we do is we say position. Isn't this tuples thing then something much more trivial? Isn't this binary digits?
I'm not sure. I'm not sure.
Isn't the set of tuples then? Okay, so that's that. Okay, so to this tuples, we want to say for each one, table of flatten a position of the thing, comma, I, I and then let's see, then what is it? Then it's length of facts. Okay, but we can actually go beyond that. We can say not only flatten the position, but we can say basically facts of this. And then to all of that, let's see what we get from this. Okay, so what that's saying is for each layer, oh no, this is wrong. Hold on, it's not length of facts, it's P, the layers there. Okay, so this should be all the ways. Okay, so what we want to do here is we want to say for each of those, it's times at that thing. Okay, lovely. So that's by layer. What happens? Okay, so those are the possible ways to get. Do you see what I'm saying there?
These are different multiplicative rules.
Yeah, those are different sequences of rules
Yeah.
that will generate a particular thing after 3 steps.
Nice.
That will generate 48 after 3 steps.
Nice. Yes.
Okay, now.
Yes.
So this is selecting. Okay, this corresponds to all ways to get to 48. Now, sampling, reducing by allowing only rules with multiplier less than or equal to 4, we would get this. Select max. There may not even be any that work here. I think it may not be possible to get this. Oh, maybe there are. Max of hash less than or equal to max of oh, come on. Oh, less than or equal to 4. Okay, there we go. So those are the rather uninteresting sequences. You see what I'm saying? Which will get to 48.
Yes. Okay. So now we have its kind of rule history in degree for 48.
Yeah, but that's what determines the rule graph. Is these different ways to get to that number.
Okay.
And the neighboring number.
Yeah.
the neighboring number is always one.
So if you take some
that has
other,
a common ancestor up to the last step, right? For which this sequence in the standard rule graph two numbers are connected if their rule sequences agree up to the last but one step. Okay.
yes. Yeah, that's fine.
Okay, so here, so what is the number theoretic version of this? We take a divisor, right? So number theoretically, the only thing that can happen here is that the last two numbers let me think about this for a second. The last two numbers have to have the same product. The last two numbers to be rulely connected, the last two numbers have to have the same product.
Wow.
Yes. i.e., pick a divisor of n that will correspond to the product of the last two numbers. Now, yeah, the number of things it's connected to.
But what does this mean more abstractly? It means what, they have like some common sub rule or something. I mean, you're just taking,
Yeah. I mean, the thing I'm trying to understand here is the relationship between the statement of where you wind up in this rule space and which rules you followed. In other words,
yes.
Is it the case that this is laying you out according to your rule sequence? And it's a little bit more subtle than that. It's not quite doing that. Right? Because okay, I'm going to take a more trivial example. Okay. The pure digits example. Okay, so what I'm saying in the pure digits example, let's see, is this thing as a digit tree? In other words, everything you land up on, do you get what I'm saying? Is let me think here. Yeah, what is the rule I think it's just this. I think it's just this. Hold on 1 second. Instead of this, it's Kn plus A, where A goes from 0 to K minus 1. And this has like with K equals 2. Okay, a happy tree.
Okay.
And then what we're doing here, so we can say with K equals 3, we'll get a ternary tree. Okay, now what we want is the branch hill version of that. Okay, that's exactly what we would expect. That's what we would expect.
Yep. Okay.
There is a nice note.
In NKS?
Yeah,
Yes.
of course. Multiplicative digits. Multiplicative, whatever. Multiplicative digit sequences. What do you know? Oh, that's a clever idea. I'd never seen these before, multiplicative digit sequences. I'd never seen this idea before. Look, a number can be specified by a list of ones which appear at the positions of the appropriate prime So I see, you're specifying a number by giving what primes appear in it. It's related. Okay, so there's a slightly fuzzy connection between this rulal space connected by common ancestry Okay, what we're actually looking for right. What we need is a thickened branch hill graph. Each thing here appears, see, those two are connected. Now, if we go back one more step, n steps back, what is connected? Well, actually, we have a hypergraph. It's Nick's, the real thing to look at is the branch hill hypergraph. Did Nick put his version of that in the function repository? Do we know? Do you know what I'm talking about?
No, the branch. When did this come up?
Oh, a month ago, maybe.
I can message Nick.
Yeah, why don't you?
Is that what it's called?
Think so.
And you want to know if it's in WFR?
I want to know. Yeah, I want to know where it is.
Okay. Okay. Mm. Okay, we'll see what he says.
I doubt he's up at this time. This would be a ridiculous time for him to be up.
Oh, no, it's only 8. It's only 8 a.m. So he might very well still be up.
Oh.
We had a meeting until
Okay. By the way, why is
9:30.
find replace path still not in the? You have got to go through the things that are in that not ready. This not ready section. You have got to go through here, work with people, and get everything in here.
Okay.
Either
Okay.
really,
Great.
I mean, this
Yeah,
is really kind of annoying that this
Yeah,
stuff is
yeah.
still sitting there.
Sure, I can do that. Mhm.
Okay, but you understand the branchial hypergraph would go not just these things here, but it would kind of wind its way back up this tree.
Yep. Yep.
And so in that branchial hypergraph, what you will see is, in fact, in this case, the precise directed sequence of rules yeah, you'll see the exact knitting together of different parts of branchial space. So we actually
Good.
definitely want that branchial hypergraph.
Okay.
But this case here, okay, so we pick a divisor of 48. Oops. Pick one of the divisors of 48. And then we say, if that isn't a prime,
Mm-hmm.
what we want is this. We want, okay, let's see. This number. So let's take 12, for example. For 12, we want divisors of 12. Yeah, okay, that's the thing we want. Those are the branchial, those are the branches. You see what I'm saying? Those are the feeder branches.
Yeah. Yeah.
Let's see, what number is it connected to again? Oh gosh, I'm so confused here. The pure product. Oh, right, right. So it's connected to a number. Wait a minute. No, this is wrong. This is wrong. it's connected to a number up to the last step. So it's basically, to be really connected,
yes,
two
yeah.
numbers can differ in their last, quotes, last factor.
Well, this makes more sense. Yeah.
Okay, so now what that means is, okay, so divisors of 48. We can pick any of those and we divide 48 by that number. So we say 48 divided by divisors of that. So 48 is connected to anything that is of that form multiplied by any other number. Right, so it's this. And each one of these is multiplied by any of the possible things we put into the rule.
Okay.
Okay, so each of these edges could be labeled by, it is the 2, 3 edge, for example. Because it's the edge which is 2 at that end and 3 at this end. See what I'm saying?
Yeah.
Each rulal edge
Yes.
is labeled by the differing last multiplicands. Okay, so we can deduce what those last multiplicands are here. So let's take this thing, for example. Okay, and so we now say edge list of this. Okay, so for each of those, we are asking, yeah, which factor differs in them? Okay.
Yeah. Okay.
Is it factor or divisor? Divisors of 10, divisors of 15. Okay, so it went on the 3 branch for one of them and the 5 branch for the and 2 branch for the other one.
Yeah.
So basically what we want to do there should be only one number for each of these. Okay, so if we say take divisors of hash, comma 2 minus 2, and let's say that's that'll be the divisors. So let's say we map that onto this. Oh God, Jonathan has this unbelievable hack. Oh God, I hate this hack. I hate this hack. We have to fix this hack. This is, again, something that should be on your project list. I mean, to get this stupid hack fixed.
I wasn't even aware of it.
Well, you see what the hack is here, right?
Yes. When you say project list, I mean,
somebody needs to do it.
No. What I was going to say is we've never discussed me doing this kind of thing before, so I'd be happy to do it. But
Which thing?
well, like asking people. I mean, I've been asking Nick to upload certain functions to the function repository, but I haven't been tasked with getting people to clean up the code before. I'm happy to do
No,
it.
but we talked about this before. This is one of the things we're trying to get the correct things in the function repository. This is one that is there before but isn't correct.
Okay.
Right? So now here, this is very weird. You see this? This isn't what I expected. I thought they would differ.
I mean, they can differ at any step.
No, but the fact is, this is at the. No, they've got to. The whole point is they have a common ancestor.
Well, they
What
have a
common ancestor does this have? See what I'm saying?
What is this? This map take divisors to expression. What is this?
I'm just getting the divisors of each of these numbers.
Oh, yeah, that's fine.
For the purpose of seeing 10 is connected to 25. Okay, that means that only at the last step did those differ. They had a common ancestor. See what I'm saying? So if I look back here, okay, let's look at this. What is the way of doing this in oh God, this is so wrong. It's so dumb. So dumb. Okay. So now the claim is that we've got a branch yield connection, rule yield connection
Yeah.
between 10 and 15. Okay, where's 10? Why the hell is 10?
I don't see it at all.
Oh, it can't be on here because it needs to go up to 5.
Yeah, okay. And that goes down to 3, yeah. Okay. There's 10. Good.
Right.
There's 15.
Where's 15?
3 to the left of 10.
Okay.
Oop.
There we go. Okay, so that is a different edge from 5 to 15.
Yes. Sure. Multiply by 2, multiply by 3. Right, and your point is they don't differ before then. Or there's a common path, but it branches at the 5.
Well, somewhat. Now, if we did this we can make this thing finite.
Oh, I see. Okay, so you have the 1 going to the 5, going to the 15. You also have the 1 going to the 3, going to the 15. And you have the 1 going to the 5 to the 10, 1, 2, 10. So you have like these two kind of planes, and they intersect at 1 goes to 5.
Okay, so what's a completion? By the way, causal invariance, I claim, is a consequence of the fundamental theorem of arithmetic. Okay, why is that? That's because no, it's even more basic than that. It's a consequence of the commutativity of multiplication.
Nick says that he did upload branchial hypergraph. It should be in the function repository.
What's it
But-
called?
Well, it's fine.
And I wonder, okay, another thing for you is, are these things getting added to the guide page of physics project functions? Oh, there is a thing called branchial hypergraph. So there is.
Also, this also means that Nick is still awake. 8:30 in the morning. Did you find it?
Yeah, I did.
I can't see it on my window.
Oh yeah, there we go.
By Nikolai Brendan. Uh,
It's a really weird way to do it, but anyway. Okay, so here what we want to do is we want to say I'm so deeply horrified to have to do this, but I think it is the best way to do it.
Well, it's a coronavirus.
The hell is that showing? Okay, hold on. What is this doing now? Okay, this is saying there's a hyperedge 235. I don't really get that. Let's try to understand this one here.
Let's see. B, C, D, fine. B, A, E.
I don't get it.
What? How do you get from B to?
Okay, branch hill hypergraph consists of order hyperedges encoding the ancestry degree of separation between an initial vertex vertices A and B have an immediate common ancestor. Oh, I see. This is all ancestry distances.
That's somewhat helpful.
Yeah, it's somewhat weird too.
Just to zoom out for 1 second. Ultimately, we're trying to, this is about the Rulliad, and you want to know, we began with the discussion of
slices of the Rulliad.
yes.
I want to know the interpretation of different slices of the Rulliad. And I also think we can build different, in this example, number of rules, time steps, initial conditions, and state value. What the heck is the analog of state value for? Yeah, it's like string length or number of atoms of space. Okay, so we can look at how the structure builds up with each of those different kinds of things. But the limiting structure, I don't really know how to make a causal graph out of this thing. I had a whole discussion of that at the end of the, I don't think this is really, the causal graph isn't the important thing here. I think, let me look at what I said in the discussion at the end of that.
I get something to eat very quickly.
What's that?
I'm gonna get something to eat very quickly.
Yeah, I'm also going to get something to eat. I'll be right back.
Yeah, good.
Either
Mhm.
try out to make the change here. Hold on 1 second. Just to make it appropriately bizarre,
Yes.
because it is a very, very bizarre thing.
What? What makes it particularly bizarre?
The Rouliad.
No, what makes the rule? No. You're what? Are these titles supposed to be bizarre?
Yeah, they're supposed to indicate that this thing is a weird object.
No. All the blog titles have this similar kind of gusto to them.
What?
I mean, no. If you're trying, I mean, what the multi-computation title was like beyond physics or something. So they all have the same kind of rhetoric to them, or same kind of presentation to them. But maybe the reality is maybe stronger.
Well, the whole point is it's like the critical priming. For example, NKS. You know, the more time goes on, the more I realize that the title was exactly the right title. But You need to prime with the title, otherwise, otherwise people are just like completely lost in what kind of a thing it is. I mean, anyway, so looking here at the causal graph question.
Okay. Hmm.
Right. Problem is, and our states don't have independent pieces. There is no distinct causal graph for numbers.
Hmm. Hmm. Do you mean that each member has a multiple real in degree? You can get there
No, I mean
different
that
ways.
the multi-way graph contains the causal information because the whole number is ingested at every step. The reason you get non-distinct causal graph and states graphs,
Yeah,
is that you don't have to do complete ingestion at every step.
right. Yep, I understand.
Now, by the way, we can do this. Let's just do the strings case. Here, what we need, I think it's just literally string replace list. I think it's just that, isn't it? Or did that do it more than once? Oh, gosh. See, this didn't just do one string replacement.
Yeah, I can see that. Wait.
Just need to look in NKS, because I'm sure I'd have an implementation there. Boy, that's complicated. That's surprisingly complicated. All I'm trying to do here is get the things labeled All right, let's try this. MW step. With that rule and list hash. No, list n. Oh, come on. What happened there? Oh, it started with 1. Silly me. Looks great. So that's labeling it with, what's that? BBB goes to. Oh, God. Okay. Okay, that's not good enough. Okay. The coloring is still wrong here. Let's see whether the multi-way system has a coloring option. Drop the mail. That's something I'm going to need, okay? Multi-way system having a way to color its different edges differently, its different rule applications differently.
Yes, that's going to come in handy.
Right.
Yep.
Because basically what we're going to get there is something analogous to this picture, but between strings.
Right.
Okay, so it's analogous to well, with strings, we have to decide whether we're leaving the strings of equal length or not. If we leave the strings of equal length, we're going to have a finite Roolead.
Which
we already drew. which we already did in other cases.
Yeah, this must look funny to someone who's not familiar with all this.
Yeah.
So it does look friendly and inviting.
I would hope.
Thanks to the good design with the Wolfram language.
Right.
So sections of the Roolead.
Right. I mean, I think that for what I'm going to write here, it's adequate to basically give a qualitative description. What I'm just worried about is these bundles of descriptions I'm also looking at the Rooleal light cone. What the heck is the right name for that? We called the other one the entanglement cone. I guess it's the translation cone.
That's what I was going to say. Yeah. So long as people can understand what's meant by translation.
Yeah, I know.
Because it's an analogous descriptor, and I wonder if there's some pithy but nonetheless more technically accurate description.
Well, okay, so wait a minute. Light cone, entanglement cone, and then translation cone. It's not really the right way to put it. It's the cone. It's the fanning out of rules cone. Is it the descriptional cone?
Well, it's our reach, or it's the reach of some observer in Rooleal space, right?
No, that's not right. That's not right. It's not right. It's the effect of an event. Some observer, but not us. We don't reach.
Okay. Yeah, we don't reach.
We're a massive particle. We don't reach the edge of the Rooleal cone. Maybe it should just be called the Rooleal cone. As coherent observers, we don't reach the edge of the Rooleal cone. Which is probably okay. At the edge of the Rooleal cone. Okay, what is Rooleal time dilation? The answer is if you have the Rooleal time dilation is interpreter slowdown.
Now, wait, no. Can we revisit the Rulio cone again?
Yeah, hold on a second.
Just
Hold
for
on, one second,
emphasis here.
1 second. Interpret a slowdown in the sense that if you have to go through an interpretation, you can't use all your computation to to move forward to just evolve in time.
Right.
Right. But actually, it's a little bit weirder because motion in Rulio space is a progressive change. See, there's something slightly wrong here. Okay, back to Rulio cones.
Okay, back to Rulio cones.
What were you wanting to say about that?
Let's just review it again, please.
Yeah, so it's just what happens in you have an event. Okay.
Oh, actually, I found it in the Turing paper. So it's you called it an emulation cone, and it's the maximal rate at which one description can be translated into another.
Oh, that's a good term. Emulation cone. See, this is one of the things that scares me. I'm writing these things so damn quickly that I'm not remembering what each of them says.
Well, good thing I asked the question about it again.
Yeah.
Okay, that's well, the only question about that is, you see, when you say the rate at which one description of behavior can be translated into another, does that mean there's a particular cone for each? Is it?
No, look. A single event produces states that are on quotes both sides of the light cone. Okay? That's all it is. Just in physical space, there's a branch pair.
Yes. Okay.
Okay.
Yep.
And what's happening here is that single event produces progressively more different states.
Yes.
And the rate at which their difference increases is determined by this. Okay, I'm going to have to go soon, but let's just do one thing, the computational analog of the continuum hypothesis.
Yes. Okay, good.
Okay. So the continuum hypothesis is you can make all the reals as leaves on an infinite binary tree. Is that the correct statement?
That's what we said.
I don't know if it's true. It'd be good to check that statement. Okay, assume that's the case. I think okay, so that's the ordinary continuum analysis. Ordinary case leaves on an immediately infinite binary tree. The computational case.
Yeah, so ALF not, I mean, ALF not is just the natural numbers.
Yeah.
Yeah.
Yeah, but 2 to the power of that
Yes.
is for every natural number, you get to decide whether you go left or right.
Right. Yes, exactly.
Okay. That's the step counter. So how do we build the computational case? Right. Here's the point. Here's the point. Here's the point. Here's the point. In this case, so in this case, you enumerate. In this case, you can get all possible sequences. Here you get all possible infinite sequences of zeros and ones.
That's right.
Okay. So now enumerate programs for generating sequences of zeros and ones. So it's a different order of enumerating all these things. For bounded algorithmic complexity, you somehow only get the computable ones. Yeah, for bounded algorithmic information content, the computable, you get the computable reals, which have the cardinality of the integers. I don't know whether anybody's looked at this limit because you get arbitrarily large programs. I mean, that's a different ordering of this limit. You're going to get the same result because eventually you're going to have a program, but that's the same type of thing that we're doing in the Roolead.
Yes.
And the point is these two cases are equivalent, but not for embedded observers or constructivist mathematicians. Because what has to happen here, in this case, your so I mean I claim that basically this case is unimplementable constructively. Or you could view it that way, that there's no, you're just picking all the arbitrary sequences.
Of course.
Whereas here you're picking sequences that can be created by a device.
Yes. I mean, 2 to the power of Aleph naught is just a combinatorial explosion that never halts. Yeah.
But I think another thing that we had talked about here, but not really covered, is kind of observer theory. Got a separate place for looking at this, where it's like where what we were looking at was imagine one is traversing a tree. How complicated is the program that determines the elements in a given foliation, etc. Anyway, that's the idea there. But all right, well, progress is being made. I think I need to go to sleep here.
Yes. I'm also very tired. I had more to say about the continuum hypothesis, but that was a few hours ago. And
what? Well, what were you?
No, no, they weren't properly formed, and I would have needed more. I would have needed to be less tired to think through them. But this is something that we'll return to.
Okay. Do you know for tomorrow? Okay.
With Nick.
Yes.
Yeah.
I mean, I'd like to, what we need next is the empirical metamathematics stuff.
Yes.
For the mathematics thing. I mean, I'm approaching the point where by the way, what should the name of the real distance unit be?
Are you searching for some cute name?
Yeah,
or
potentially. I mean, I don't know. I mean, the real distance.
You have more of a penchant for that than I do.
Real distance units.
I mean, I'd like to think of it in terms of operations, but I know you've looked at it before in terms of tokens per second.
No, that's the rate. Yeah, the radial distance unit is the size of interpreter necessary to get from one position in real space to another.
This is getting pretty Chaitin-esque.
Yeah.
It's very, very Chaitin-esque. Holy moly. I wouldn't have dared say something like that.
I know. I'm telling you, I knew this was converging. That's what I said at the end of that real Turing machine thing.
Yes. And during the talk with Greg when he was at that Mexican hotel.
Yeah.
Okay, what were you saying about? Okay, so with Nick, so I had a quite long working session with Nick yesterday. Nick has made some nice steps in what Nick wants ultimately is something where you can kind of translate back and forth between metamath and Wolfram language. And metamath poses its own challenges based on some kind of strange ways in which it actually encodes one thing or another. But Nick, it's found some interesting ways of actually representing it, even though MetaMath has a specific way of doing it. And then we also spent quite a bit of time on this. Oh, what is it called? What did you call it? It's for these TWPs. It's like not pattern finder. What did we end up calling it?
Two-way patterns.
No. It has a specific. I mean, the name itself is not particularly important, but there was something that you asked specifically to be done, and progress was made on that too. We had a quite intense. That's part of why I'm tired today as well. We had a quite intense meeting.
Look, I will be available tomorrow starting around noon my time. So I'm available from noon until 3 my time. Then I'm not available from 3 until 6. And then I'd really like tomorrow evening to work on actually writing some pieces of this thing. But let's just talk about radial distance units for a second, okay?
Well, in terms of meeting, let's think. So you said you could meet beginning at 6?
Potentially, yes.
It would be better. That would be better for me.
Okay. All right, fine.
It's 3 my time. And I'll send Nick's aware. He's aware of the meeting, so he won't be surprised. And he said he'll be available.
Okay. All right.
And
I might have to. Okay.
Mhm.
I'm sorry. I just want to come back to radial distance units.
Mhm.
That's pure algorithmic information. That's the pure. Well, it's not quite that. It's the size of the interpreter. It's the prefix to the program necessary to get from one position in radial space to another. And so, yeah, this emulation cone is the outer distance that you can get to after a certain time. You can get that distance actually it's not the size of interpreter. It's the or is it
I mean, I'm a little nervous
steps.
about. I'm a little nervous about. Yes. Yeah. Number of
steps necessary to do the translation.
Hello, that's what I said when I said it's operations. Yes.
Okay. You're right. I think you're right. It's the number of steps. You're right.
This is why, and I'm taking it from time complexity. It's just the time complexity of the translation, which could involve some simple rule. Though it might take longer. That's the other thing, is there's some relationship between the
time complexity of the translation, the minimum time complexity is the geodesic, is the radial space.
Nice. Oh, well, wait, let's explore now what this all means, because geodesics play an important role in the physics project. Let's think about this.
Well, this is a geodesic within radial space itself.
Yes, I know. But just thinking about how,
as opposed to space-time, this is a different issue. This is like a single spatial look. This is in a single radial slice. Well, this is in a single time slice. One lays out all the results for different sequences for different rules. And there is a geodesic distance in radial space between different results, between different rules, basically. Yeah.
Yeah. I mean, there are possible different. Are there possible D6, or is there just one?
There could be more than one. There could be all kinds of that. There can be all kinds of. I mean, which is whose length is the time complexity or the operation complexity, time/operation complexity of the transformation from one rule to the other, or at least from one rule result to the other, because we only got a single result in this time slice.
Does that mean that something like Solomonoff induction is like the equivalent of the quantum amplitude on these Rulio geodesics?
What is Solomonoff induction?
Well, so with all this like quantum probability, where you're taking the smallest program that could give you a particular result. I'm just thinking of because we had the magnum of quantum amplitudes as assigning different path weights to geodesics in the physics project.
Right. But the question is what the right. But in that case, the phase is the position in branch Hill space. So, do you have an analog of that phase?
Phase is the position in branch Hill space.
Yes.
So we have to have a position in Rulio space.
And what is, I don't know what Solomonoff induction is, even though I certainly met Ray Solomonoff. But
oh, you've met him?
I did, yeah. He came to our conference in 2003, I remember.
Oh, wow. It's a way of when you're weighing between different possible theories, it's kind of like Occam's razor, but for algorithmic information theory. You're taking the smallest possible description.
Yeah, that's right.
And that's why I was thinking if there were multiple geodesics for, say, different rules, and those geodesics differ in their time complexity, then
But they can't both
Solomonoff.
be geodesics.
Well, yeah, well, then this doesn't work then.
Right, but the question of what the interpretation of position in Rulio space is in terms of anything else is interesting. And we've got a distance in Rulio space, but the geometry of Rulio space is what the non-trivial thing is. Right, that's the issue, is the geometry,
Yeah, that's worth writing down.
Geometry of Rulio space is how to lay out possible programs in a geometrical way. Right, that's the issue. That's the thing that we also have in quantum mechanics. It's not obvious how to lay out the states in quantum mechanics in a geometrical way. Do you get what I'm saying?
Yeah.
But what we're trying to do by making branch Hill graphs is to deduce that layout.
Yes, right. I understand.
And similarly, we don't know it for Rulio, the Rulio case. Well, it's very interesting. What it basically, this whole thing is basically telling us is, well, it's a bit of a disappointing result that there is no fundamental theory of physics.
Isn't there some kind of hint at this in the introduction to the Wolfram Physics Project near the end?
Yes, there is.
Yes. I remember reading that. And then I remember reading about what people said about the physics project. And I concluded most of the commentators hadn't read to the end.
Some had, though. Some people really understood that stuff. Some people actually really understood that much better than I expected. But this particular point, the basic point here is so bizarre. Did not see this one coming. That basically the theory, general relativity, is a fixed theory. But its interpretation in terms of measurable things is up to the observer.
Sure.
In other words,
the
problem is not
I see where this is going. Yeah.
derivation of general relativity. The problem is how you map that derivation onto what is measurable to humans.
Right. So the aliens also have relativity, but they just they just experience time in a different way. On the other hand, theories become less fixed as soon as you consider Rullial relativity, so to speak.
Yes, that's right. Okay, so the basic point is no fundamental theory of physics, but general relativity is generic to all theories except, but its interpretation in terms of degrees of freedom, in terms of measurable degrees of freedom, is what differs. And that's exactly why multi-computation works, because the immune system has its own version of this.
Still haven't really probed that much, but I'll just take your word for it for now.
Yeah. So what were you saying about how, I mean,
I said what the last thing I said was, so some extraterrestrial non-human observer is also still answerable to general relativity, but they experience time in some way depending on the mass of the planet they're on or what have you.
Well, on the other hand, time, but they experience everything. They experience their parsing of space may be different. Whole thing may be a total mess.
Fine. But there's some Rullial relativity. And this is then this makes us that theories really are not necessarily generic. There's some non-genericity in Rullial relativity. That's the idea, right?
Non-genericity. Okay, hold on. Rullial relativity is the statement that there is a general relativity for everybody. But one may have different, in other words, Rullial relativity says that the quotes, the laws of physics are the same for everyone, which really means everyone has GR, but in a different frame, but in a different Rullial frame.
Okay.
So in other words, there is a general relativity, but it applies to, some bizarre thing in linguistics about the use of words. By the way, I am getting closer. Words are equivalence classes.
Getting closer to what?
Oh, the understanding linguistics in a multi-computational way.
Oh, well, that wouldn't be surprising.
So it would be or would not be surprising?
No, it would not be surprised. I'm going to be surprised by very little.
Yeah, well, I think
at this point, Stephen,
the sad part will be right around the time when the pandemic is over, we'll finally figure out immunology and have something interesting to say there.
Well, the sadder reality is that will actually probably still be useful in the future, because this is not going to be the last.
It's been 100 years since the last one, but
sorry,
it's been 100 years since the last big pandemic, at least in the US.
Yeah.
Anyway,
well, so long as you think that we're going to survive for the next couple of 100 years, then
I'm not going to be around, so at least not in
well,
current form.
mm,
So
let's just see, let's see what we can do with multi computation and medicine or something.
yes, well, right. That's a computational irreducibility really bites there. Plus, and anyway, all right, I should go and
Wait.
closer.
Yeah? Trying to implement some no cliffhanger rule here. Weren't we in the middle of something? Let's just finish it and then.
No, we were not. We were just talking about. I think we pretty much finished this, and I mean, basically, in terms of the structure of what I'm trying to write, I wanted to have a decent example of a Roolead construction.
Yeah, I think that would be really helpful.
It's going to be fairly complicated, and I mean all the different versions. I think this one with multiplication numbers is a reasonable one. I think what I'll do is show that one and show the one with strings. Maybe I'll show the one with Wolfram models as well. Why not? What the hell?
Why not? Yeah. Okay, so meeting tomorrow with our friend Nick at 3:00 your time.
3:00 your time, 6:00 my time.
Good. Yeah. Better. 6:00 your time, 3:00 my time.
Okay. So I'm still trying to understand. Yeah, I think I'm pretty good on most of this stuff. I think that the part of this. Okay, in the mathematics case, I just need to know more empirical mathematics. And then I'm trying to understand what homogeneity in the mathematical universe looks like and other aspects of that. All right.
That seems very relevant to what we've just been looking at.
Well, I know, but the point is,
yeah.
Look, everything is related to everything. Okay.
No, but non-trivially related.
Sure. Yeah, that's right. But I mean, what I want to do is write about the Roolead without writing about all the mathematics.
Yeah, I understand.
And use the Roolead as raw material for writing about mathematics, because there's different ways into mathematics. By the way, another feature of the Roolead is I have to be very careful not to talk about the evolution of the Roolead, because the Roolead is
just there.
Is a necessary object.
Well, how would you fall into some trap of talking about the evolution of it?
Well, I mean, it's the construction of the Roolead is what constructs the Roolead, and the answer is the Roolead is a necessary object.
It's just there.
It's just there, and we are merely.
And well, the whole point, as I understand it, is the impulse to construct anything is just a result of our computational boundedness.
Explain.
Well, this is what we were discussing before about the Turing machines in the continuum. Is that we're
I see what you're saying.
We're trying to make these
outside. Yeah, right. If we were on the outside, then it's just like, well, we're done, but it's very boring.
Right.
In other words,
you don't have to construct it if it's given. If you're on the inside, you have to construct it, but you actually can't in full. So it has this awful Sisyphusian quality to it. Ultimately.
Well, yes, but the point about it is, from the outside, the universe is completely boring.
Yeah, but no one's actually bored because those observers don't really exist. So that's the happy spin on it.
On the outside, the universe is boring. The Roolead, i.e., universe of all possible universes,
Roolead. Yeah. I think Rulliad's actually probably the best name of all.
It's a nice name. Yeah, it's a
It
good
reminds me of the Stanislaw Lem Siberiad science
what that
fiction
is.
book.
I was thinking it reminded one of some of those ancient Indian literature things that end in ad.
Well, maybe Lem had a similar impulse.
Okay, from the outside, but we are forced to explore in a computationally bounded way.
Yeah. So we're not bored, but we also don't get to see this
Right,
whole
right.
thing.
So we are not bored, and our efforts are, quotes, meaningful because of computational irreducibility. That is why that's why it's non-trivial. That is why it is difficult to explore the Rulliad.
And if there wasn't computational irreducibility, then being on the inside wouldn't be that different from being on the outside, which would mean.
Yeah, that's a good point. Right.
And
without computational irreducibility, the inside and outside of the Rulliad would be similar.
Which would mean it just wouldn't have that many rules in it in some way, right?
Yeah.
Yeah.
Computational irreducibility is the reason that there's infinite diversity.
No, it's the other way around, because you have to start with the Rulliad, because that's the pre-given thing. So it's because the Rulliad is so fertile in terms of rules that you have computational irreducibility, I think. If you have some fixed pre-given object in your theory, you have to start your causal explanations there, because that's kind of what you have it there for, right?
I don't agree. I don't agree. That's the top-down, bottom-up issue. And I think that's really confusing, because it's like, what's the point of, I mean, that's constructive versus non-constructive mathematics. Do you start your explanations with what you can construct, or?
Well, it's difficult in this case because we're talking about individuals who are attempting to make constructions.
Do you start from what you can construct, or do you start from a non-constructive object and then see how to look inside? All right, this is exciting stuff. I mean, oh my gosh, there is too much to do. You know, there's just way too much to do.
Yes, don't worry, I know. But you're right. I am a little spoiled. It's a very fruitful time, and this fruit will probably just beget more fruit as well.
I suspect so.
That's how fruit works.
Right. Yeah, right. That's kind of its point evolutionarily. But I mean, my prediction is there's at least 5 years of rapid growth.
Wow.
'Tis the way of such things. This is the dividend of a paradigm.
Yeah.
And this is kind of, I think multi-computation is actually the core paradigmatic idea.
Well, that's what you stated.
Yeah, I know.
No, I know you know, but you're saying it as though it was something you just thought of.
No. But I mean, I think that's the thing. That's the thing that has at least 5 years of low-hanging fruit.
By the way, and not to get this final question, in terms of the email that you get, I mean, you get email about all kinds of things, but are you getting a steady stream of email of interest in multi-computation and these new ideas? I mean, I get some of it from you, but I don't know the.
Yeah, I'm getting a reasonably steady stream of, I mean, look, this stuff about the Rulliad, this is pretty high philosophy. And I mean, you know, if you thought category theory was abstract, this is pretty highly abstract and highly philosophical.
I like the abstract. I find it much. I find it much easier to work at that level.
Well, look, the fact is, the thing we really have to do is make multi-computation, make a multi-computational language design. And that's where these two-way rules, the two-way patterns and so on are important.
Yeah.
And yeah. No, I mean, what's interesting about this is paradigmatically, the idea of symbolic transformations on expressions and so on has been a slow burn paradigmatic idea for me. Multi-decade slow burn paradigmatic idea. The simple programs idea was a slightly faster burn. That is, if you look at, I mean, that was a very definitely, unfortunately, it's 10 plus a bit person years was the main, or 15 plus a bit, I mean, plus a few other people, but it was primarily my efforts. So it's kind of explicitly measurable. That was the time it took to pick the low-hanging fruit.
Sure. Don't you even have it measured in like mouse miles?
Yeah.
In this kind of thing.
Yes, I do.
Okay. No, one more question. This is just the historian in me. I've always wanted to know, when it said Wolfram spent a decade in isolation working on NKS, what does that mean? I mean, you had a company. What does, or like a decade in self-imposed exile or whatever? These are like the descriptions. What does that actually mean in practice?
Well, I was first in California and then in Chicago, and I visited the company like twice a year. But I've been a remote CEO, so I was working, I was doing company stuff for some number of hours per day, plus dealing with email.
Yeah.
And then, but I didn't interact with people outside of, I mean, I interacted with company people, but I didn't interact with anybody else. Zero.
You didn't send mail to anyone you had interacted with at Caltech or Princeton or?
No, I did at the beginning, and I just got back too many questions, too many, what about this? What about that? And I just sort of gave up because I said, I don't really need these questions. I've got a good enough path. There's a path that I know I want to follow. So why don't I just go and follow that path, and then the people can ask the questions at the end. I didn't need their questions in working out. I mean, I already had. Honestly, this stuff now is significantly more difficult than the early NKS stuff. The early NKS stuff, in a sense, was a much straighter shot.
You're less alone now. It seems to make this easier in some way.
Well, it does, yeah, but it does. But the fact is, I think I wouldn't be able to do this stuff purely on my own. Now, perhaps that's because I'm older. I don't know. I don't think so particularly. I'm a lot more experienced.
What's interesting is that you basically receded for a decade, but you're so well connected now. I mean, that's quite interesting. It's not like you stopped talking to people for 10 years and then you were never able to regain your social
Look, you
connectivity,
know
you
what?
got it back.
When I meet people that I haven't seen in 50 years,
Yeah.
it reconnects quickly.
Yeah. Yeah.
I mean, no, there are people who sort of grew to prominence during the decade that I was away, who I don't know, who I sort of only pre-know, so to speak.
I see. Yes, because you weren't in the loop
Yeah,
at that time.
yeah,
But people beforehand, you just got back in touch with them.
yeah.
And afterwards, it didn't matter. Yes, I see.
Right.
Okay.
And the fact is that there were people where I'd sort of had some interaction with them, then they became more relevant to me, but it then took more work to reconnect after that period.
Hmm.
I mean, the truth is, most people, well, there also wasn't a lot of, I mean, other than people at the company, it wasn't like there was summer schools and things like that where I was getting a big stream of new people coming in.
Right.
And I mean, remember that period of time coincided with when the web started. There wasn't the web at the beginning of that time. There was no web,
Right.
and I mean, it was literally, all my documents were on paper, copies, photocopies of tons of articles, et cetera, et cetera, et cetera. And as the book was finished, I mean, I had, my office was covered with piles of paper, and as the book finished, those piles receded until eventually the floor was clear, and then the book was done.
Hmm.
It was quite visual, actually. And every section had a pile, basically.
Right.
And no, I think what's happening now, this is significantly more conceptually difficult than NKS was.
Wow. It's interesting to hear that.
Yeah. I mean,
I mean,
look,
it probably won't be one book, right? You've
this
already
stuff,
you already have one book. I mean, I guess it's a shorter book from some of the blog posts you've made recently, and you have the physics book.
yeah, I know.
So this is
Yeah, I know,
multiple
but these are
volumes.
also not as tight. These blog posts are not nearly as tight as the NKS book. The NKS book was very minimalist. It'll say things in 3 pages, which now I would say in 25 pages. And it was more filtered, but it's okay. I mean, it's no, I mean, this stuff is more abstract and more it's also, I don't know, it look, the thing that's really weird about this stuff for me right now, it's going so fast. I mean, with the NKS book, I sort of, every page is something I remember pretty much. I remember doing it. Whereas I'm looking at these posts I'm writing now, and they were generated so quickly that they're pieces where I'm like, oh, that's interesting. I forgot that I figured that out, 3 months ago or something. But I don't think that's, I mean, I think it's a better calculation to get these things out quickly than it is to, okay, the other thing that's happened is, I would say that I've always been a decent expositor, but I've been getting better and better at that. It's not hurt by these, doing all these live streams and things.
Right.
That's a tremendously good exercise. I mean, I wish I'd thought of that years ago.
Well, you
It's
couldn't have done it when you were writing NKS, especially at the
no, they
beginning.
didn't exist, right? The things
Right.
didn't exist. No, I mean, this is the dividend of sort of technology. And I mean, look, I was a remote CEO. That was a weird thing back in 1991. And I was using, web conferencing, web
Yeah.
screen sharing stuff,
Yeah.
phone plus screen sharing. back in 1991, 2 type time frame. So it maybe a little later than that, but I mean, so the world has definitely moved in my direction in that regard, but I just had not internalized the value of I mean, literally this exercise of I sit down, I stare at the camera, I read the questions, I try and answer them.
Yeah.
You know, it's a really good exercise. I mean, like people asked me, like there was one this last time that was, what is the relationship between sort of the public visibility of scientists and the significance of their work? I think my answer was fairly interesting. I mean, I answered a bunch of historical stuff and, you know, talked about how different attributes of expository skills and, you know, the extent to which expository skills are necessary to do good science. And, you know, otherwise you don't understand what the heck you're talking about, but you only have to be able to explain it to yourself. You know, you don't have to explain it to anybody else for that purpose. But anyway, it's a super good exercise. This thing about, I mean, it's better because it's very unforgiving. That is, I know every successive word I'm saying is getting live streamed, it's recorded, et cetera, et cetera, et cetera. It's not like one of these things where you just sort of, I mean, I'm trying pretty hard to speak in full sentences and not to go in loops. And that's more difficult than doing it, you know, in person, sort of teaching something, because really when there are actual people right there, even on a Zoom session or something, you can sort of say, oh, well, I don't know, that doesn't seem right, I'm going to go in a different direction. But I'm not doing that in this case. I'm just barreling forward. And it's a good exercise, and it's really helped my ability to explain. Plus all this writing of all these blog posts really helps. And it makes it, I mean, this particular thing, explaining this particular Rulliad thing, this is not the world's most trivial thing to explain.
No.
And I think I'll probably get an explanation that a bunch of people will understand.
Will?
Yeah, will understand.
Yeah.
Yeah, they will understand it. Just like the multi-computation piece, people can understand it. I mean, it's not like it's, and that could be unbelievably incomprehensible.
Without any actual computational examples, it wouldn't be. Just like many of the articles that are in the Journal of Complex Systems, for instance. I mean, having a way to visualize computation is just a very important tool.
No, I agree.
And the fact that we have people that can make it so that we can literally, I mean, I think that this is the way in which it really is being spoiled, is like working with Nick and probably other people too. You have an idea of a kind of a computational system where you want to represent some aspect or some behavior, and then it's just there.
Yeah, I know.
It's amazing. It's amazing, Stephen.
Yeah,
anyway, the context, this whole context is very helpful. I've wondered, I mean, I don't have the context of exactly what's special about this particular moment. It seems quite special. So
yeah,
let's keep going.
It's cool. I mean, it's look, I think that the challenge organizationally, okay,
Yes.
is this, that each of these things, you know, immunology, experimental implications of physics project, each of these things, I mean, I hate to sound corporate about it, but these are all verticals, if you understand what I'm saying.
Yes.
Right? And the problem is that each vertical needs a certain critical mass of people. It's not enough to just have, you know, each vertical needs a certain, just having, you know, each vertical needs a certain investment. Like the chemistry thing, you know, chemical computing thing. I guess we'll get to that I mean, I don't know in what order we're going to get to these things. I mean, it's just totally crazy because we're going to get, we got, okay, it's this week we're going to do meta mathematics. It's next week we're going to do molecular computing. It's quite wild.
Oh,
And those things,
it's very wild, and everyone has something else, many other tasks they're already attending to. I mean, Nick's an interesting example because it's not as though he's not busy. He's just at Wolfram Solutions, and he really likes working on this, contributing towards the conceptual projects.
yeah, I know.
So he's just, I mean, that's what I like.
Right. I mean, we're all a bunch of, yeah, right. I mean, this is the amusing fact, is that we're all a bunch of amateurs at some level, in the sense that there's essentially nobody who is, fully, but I mean, look, the organizational problem is each one of these things, like with the immunology thing, we haven't even contacted a single immunologist yet. But any immunologist needs to be heavily enculturated, and it may not even be possible. I mean, they may be too far away in rural space, so to speak, to reach.
Well, but I wasn't going to say that Nick is an amateur. What I meant is that Nick is very busy, but he just finds the work really interesting, and so he just sets time aside anyway.
Yeah, I realize. Right.
But the problem is it's even for people who really like the projects, it's just difficult. Like Xerxes, I'd like Xerxes to be on all kinds of different meetings. He can't. At least it doesn't seem as though he can be included more often. I'm still fishing for more people on whom I can rely. I mean, research assistants, Sarah and Ariana. I mean, I work with them on certain tasks, and they just have it's quite clear what they have to do. With these other projects.